Alright, finally the final chapter of general physics, which is going to be pressure here. Look at the first question, what do they want from you? Four different liquids are poured into a container. The diagram shows the depth and the density of liquid in each container. In which container is the pressure on the base the greatest? Now today, if you remember the formula for pressure in a liquid, pressure is equals to rho GH, right? Density, gravity and height, right? Whichever one has the greatest density and the greatest height is usually going to be the one that has the greatest pressure. Looking at this information here, this one has the greatest density, but this one has the greatest height. So I guess we have to do rho GH for each and every one of them. Rho GH for this one will be 3.1 times 10 times 10 here, which will be 310. This will be 1.2 times 10 times 20. This will be 240. This will be 1.3 times 10 times 30. 390, and finally 0.8 times 10 times 40 here. This will be 320. So the answer is going to be C for this one here, guys. Alright, then after that, moving on to the next question. This one here is basically a combination of moments and also pressure, guys. Looking at this question here, what do they want from you? Figure 2.2 shows the brake pedals for the vehicle. The driver exerts a force on the pedal which increases the pressure in the oil to operate the brake. The area of the piston in the cylinder is 6 blah 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 blah. This will be the area here. The pressure increases the oil. Increase in the oil is this amount here. This is going to be the pressure. Calculate the force exerted by the driver on the brake pedal. We're looking for this force here. But okay, this is what the students usually get wrong, guys. Straight away, right? Looking at the question here, they'll think that, oh, I have pressure, I have area. I'm going to do the pressure equals to force over area formula. So force is equals to pressure times with area. And straight away, they're going to multiply these two things together, and they're going to give me the final answer for this one here. Now, this is definitely not true. While it is true that the pressure is force over area, and you can find the force using pressure times with area, the force that you find here, right, will be this force that you're looking for instead, because this pressure is from the oil, this area is from the piston here. So you have to be very careful about what information you're looking for. Based on this formula here, pressure times with area, which is going to be this one here, the force is going to be 325 newtons. 325 newtons is this force here instead. Now, like I mentioned, this one here there's a pivot in the question, right? If there is a pivot in the question, it is always going to indicate that you are supposed to solve it using moments, guys. And since there's one force here that acts in the clockwise moment and another force here that acts in the anti-clockwise movement against the pivot, I can simply use the moments in equilibrium formula, which states that the total anti-clockwise moment is equals to the total clockwise moment. From here, it's just a matter of force multiplied by 24, always distance to the pivot, is equals to the force multiplied by 335 multiplied by 7 here. So in order to find F, is just a simple algebra expression, 325 times with 7 divide by 24, and you're supposed to get a force of 94.8 newtons. Always remember, you can only write 3 significant figures in these kind of answers here, so you're going to write 94.8 newtons here, and this is how you get the final answer for this question here. All right. And then this next question here, a balloon contains a fixed mass of gas. Explain in terms of momentum of molecules how the gas in the balloon exerts a pressure. Now this question here is basically testing your understanding on momentum and also pressure. You're supposed to formulate a formula and relate them all together. Now moment is basically going to be mass times velocity, right? It's supposed to be mass times velocity. Pressure here is supposed to be force over area, right? Now, looking at these two formulas, they actually have no correlationship, but if you recall back about the impulse formula, which is going to be Ft equals to mv minus mu, right? You'll understand that force is actually going to be mv minus mu over t, right? So from here, how am I going to relate all these things here? The force that is exerted inside the balloon, right, depends on the change of momentum, in a sense that a greater change in momentum is going to generate a greater force inside the balloon. This greater force will also increase the pressure inside the balloon as well, guys. So you're supposed to use these formulas and relate everything together. So if I were to answer this here, I'll say that as the molecules collide against the walls of the container, the increase in change in momentum of the molecules increases the force exerted on the walls of the container, thus increasing the pressure in the balloon. You're supposed to write something down like this here, guys. Alright. Then this next question here is similar from the question we did just now. In the braking system, blah, 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 yet again you see the word pivot, so straight away you must think about moments, guys. The driver exerts a force of 200 newtons. It is a distance of 22 cm away. It rotates the pivot, blah, blah. The area of the piston is this amount. The area here this time is this amount. Calculate the increase in pressure of the oil here. Now, first and foremost, we are supposed to find the moments in equilibrium in this question here, because we are supposed to understand that the moment generated by this force here will be the equals to the moment generated by this force here. So, moments in equilibrium, yet again, total anti-clockwise moment should be equals to the total clockwise moment. From here, anti-clockwise moment will be force multiplied by 8 is equals to 200 multiplied by 22. From here, the force will be 200 multiplied by 22 divided by 8. Press that into your calculator. You're going to get a force of 550 newtons. You're supposed to get a force of 550 newtons here. With this 550 newtons, if you want to find the pressure this time will be force over area, right, which is going to be 550 divided by the area of 0.0005. So if I divide this with 0.0005, I'll get a damn big pressure, which is 1.1 times 10 to the power of 1, 2, 3, 4, 5, 6. 6 pascals. 1.1 times 10 to the power of 6 pascals here. Alright? Then moving on to the next question here. A diagram shows a stone suspended on a string under the surface of a liquid. The stone experiences a pressure caused by the liquid. What would increase the pressure of the stone? Yet again, the formula here is going to be rho GH, right? Increase in pressure will either be because of the increased intensity or the increase in height of the water column above you. Right, so decreasing the surface area, not logical. Increasing the mass, not logical. Lowering the stone deeper into the liquid, definitely logical, because when I lower the stone deeper into the liquid, the height of water column above it is greater, right? And ultimately, this is going to increase the pressure here. Then, a cube of side 0.04 meters, it's a cube, so I can assume that the height, the width, the base, the height is all the width, the length, the height is all going to be 0.04 meters. It's floating in a container. Figure 3.1 shows the surface of the liquid is 0.028 meters. So this part here is 0.028 meters above the level of the water. The pressure of the air above the cube exerts a force on the top of the cube. The valve is closed. Explain in terms of air molecules how the force due to the pressure of the air is produced here. So this question here, yet again, they're asking about how the force is produced from the air, right? Now, yet again, in these kind of questions here, you must always relate back to your formula, guys. So this question here is actually asking for you guys to find the force due to the pressure, right? Yet again, you're supposed to understand that pressure is equals to force over area here. Whenever there is a pressure on top of this cube here, it is essentially due to the forces of it, right? And so you can ask yourself, what are the forces that are responsible for this pressure here? It is yet again the air molecules consistently colliding against the top of this cube here, producing that force. So if you're supposed to write this down, it's going to be something like the air molecules from the surrounding is consistently colliding against the top of the cube here. This produces a force per unit area on the cube, ultimately increasing the pressure on top of the container here. Okay, the air molecules from the surrounding is consistently colliding against the top of the cube. This produces a force per unit area on the cube, ultimately increasing the pressure on top of the container here. Alright? Then, after that, the density of liquid in the container is blah blah blah. This is the density. The pressure due to the liquid at depth, blah blah blah. This is H. Very straightforward law. This one here, they already have density and height, right? So pressure is essentially going to be rho GH, right? Which in this question here will be 1500 multiplied by 10 or 9.8 if the new syllabus, right? Multiplied by 0.028 here. Press that into the calculator. 1500 times 9.8 times 0.028. You'll get a total pressure of 412 pascals. You're supposed to get 412 pascals here. And finally, the last question here, the force on the bottom of the face caused by the pressure due to the liquid. So if I have force, I have pressure, right? All I need to do is use pressure equals to force over area here. Force will be equals to pressure multiplied by area. The pressure here will be 412, right? The area would have been how much? 0.04 times 0.04 because it's a cube, right? So it's basically 0.04 square lah. Press that in the calculator again. 412 multiplied by 0.04 multiplied by 0.04. You'll get a force of 0.66 newtons. You're going to get 0.66 newtons here. Okay, 0.66 newtons here. Then after that, figure 3.1 shows a small submarine submerged below the surface of the sea. The density is this amount. Calculate the pressure when it is this amount below the sea. Yet again, pressure is equals to rho GH, which is going to be 1030 multiplied by 9.8 multiplied by the height, 3 times 10 to the power of 3. Oh, press this into your calculator, you're going to get 1030 times 9.8 times 3 times 10 to the power of 3 here. Oh, you're going to get a damn big number. It's going to be 3.03 times 10 to the power of 7 pascals. 3.03 times 10 to the power of 7 pascals here. Alright, then moving on to the final exercises. Diagram shows a solid block resting on a bench. The dimension of the block are shown. On which labeled surface should the block rest to produce the smallest pressure? Pressure is equals to force over area. In order to have the smallest pressure, I need to have the greatest area, right? So looking at this, logically speaking, obviously P should have the greatest area here, right? Then the pressure due to the liquid on an object immersed is this amount. This is the pressure. The density is this amount. What is the depth of the object below the surface? Pressure is rho g h. H will be pressure over rho g. Right, so if it's pressure over rho g here, it will be 4500 divided by 900 divided by 10. You'll get exactly 0.5 meters. Guys, you're supposed to get 0.5 meters, which is essentially going to be 50 cm. Don't circle A. It's a big question now, guys. Alright, then an object is 60 cm, which is 0.6 meters here below the surface of the liquid. The pressure due to the liquid at this depth is this amount. This is pressure. What is the density? Pressure, yet again, rho GH. Pressure over GH is equals to density. So it's 9,000 divided by 10 divided by 0.6 here. You'll get 1,500 kgs per meter cube. Be careful with your units, guys. Always make sure you change it to the proper units. A pipe full of water connects a water supply, blah, blah, blah. The length of the pipe is this amount. The height of the supply above the tap is this amount. The density of the water is this amount. The effects of atmospheric pressure is negligible. What is the water pressure at the tap? Oh, the length of the pipe. The density of water is 1000 kgs per meter cube. The effects of atmospheric pressure is negligible. Ooh. Well, I'm having a hard time imagining how this pipe is. Is the pipe going to be like this, or is the pipe going to be downwards like this? Pipe full of water connects a water supply on a hill to a tap lower down the hill. A pipe full of water connects a water supply. The length of the pipe is 500 meters cube. The height of supply above the tap. The height of the supply above the tap. What the hell? Okay, after lots of thinking and a few drawings later, I kind of understand what this question is already. It says that, so there's three parts here, right? There is a pipe, there is a water supply, and then there is a tap. This pipe that is full of water is connected to a water supply on a hill to a tap lower down the hill. So there is a pipe. It is full of water that is connected to a water supply that is connected to another tap at the bottom of the hill. They say that the length of the pipe is actually 500 meters, which is actually irrelevant. The height of the supply above the tap is 100 meters. The height of the tap above the water supply, the height of the supply above the tap is 100 meters here. So then after that, they give us the density and they're asking about the pressure at the tap. Now you have to understand that the pressure of the tap is supposed to be the vertical distance that is affecting the pressure, right? So from here is basically just pressure equals to rho GH, which is going to be 1000 multiplied by 10 multiplied by your 100 here, which at the end of the day will give you 1 million pascals instead. Okay, it's just a matter of misunderstanding of the question's style. Alright, then looking at the final part of this exercise here, Figure 3.1 shows gas trapped in a sealed tube by a dense liquid. Blah, blah, blah. The scale mark on the sealed end on the tube is calibrated to read the volume of gas trapped above the liquid surface. Figure 3.1 shows that initially the volume is 60 cm cube. So initially here is 60 cm cube of pressure of gas lah. Then the pressure of the atmospheric pressure, the pressure of the atmosphere is this amount. The pressure of the atmosphere is this amount. State how figure 3.1 shows that the pressure on the trapped gas is equals to the pressure of the atmosphere. Now as you can see, these liquid levels, they are both equal, right? If this equals, it means to say that the pressure on the left side would have been equals to the pressure on the right side. So if you're asked these kind of questions here, all you have to say is that the dense liquid has same levels on both sides of the tube. Okay? Then explain in terms of momentum of its molecules why the trapped gas exerts a pressure on the wall of the tube. Yet again, you can see that this is quite a famous question. Looking back at this question here, you have to understand that pressure is equals to force over area, and force is yet again change in momentum over time. So you're supposed to say something that as the gas molecules collide against the wall, they change in momentum, increasing the force. This force is consistently the air molecules are colliding against the walls of the container, increasing the force per unit area and ultimately increasing the pressure. It's always going to be a 3-mark question. So you're supposed to say as the air molecules collide against the walls of the container, it changes momentum and produces a force per unit area in the tube. This causes an increase in pressure. Okay, this is how it's supposed to answer these kind of questions here, guys. Right? Then the final part here. A scientist fills a container with seawater. The container has a dimension of blah blah blah. The density is this amount. Now first thing I notice is that this is in cm and this is in meters cube. So you have to change everything into meters. 0.3 times 0.3 times 0.4, which is going to give you how much? 0.3. Yeah. Why is this so big? 0.3 times 0.3 times 0.4, which is going to give you a volume of 0.036 meters cube. From here, you have density, right? Density is equals to mass over volume. Mass will be equals to density multiplied by volume, which is going to be 1020 multiplied by 0.036. Okay, times 1020 here, you'll get a mass of 36.7 kg. Right, always remember to write it in 3 significant figures. Then the atmospheric pressure is 100 kPa and the total pressure on top of the surface is 500 kPa. So basically there is 2 parts to it, right? The atmospheric pressure is 100 kPa. The total pressure is 500 kPa. Calculate the depth of the top surface of the submarine below the surface of the sea. Yet again, pressure is equals to rho g h here. If I want to find a h, which is the depth, it's going to be pressure over rho g. In this case here, the pressure is supposed to be 500 minus 100 because this is 500, this is 100, right? The pressure due to the sea is only this mark, which is your 400 kPa, right? So it's 400,000 Pa divided by the density, which was 1020, multiplied by gravity, which is 9.8, right? So press that in the calculator. 400,000 divided by 1020 divided by 9.8. You're going to get a depth of exactly 40 meters here. Alright. Then finally, a hatch opening door on the top of the surface of the submarine has an area of 0.62 meters square. Calculate the downward force of the hatch due to the total pressure. Now if they talk about total pressure, then obviously we're going to use 500 kPa here lah. Pressure is equals to force over area yet again. Force will be equals to pressure multiplied by area, which will be 500,000 multiplied by 0.62. 500,000 multiplied by 0.62. You'll get a force of 310,000 newtons, which is 3.1 times 10 to the power of 1, 2, 3, 4, 5 newtons here. Okay? And this is how you're supposed to do the pressure questions.